So today we are going to move to this topic which I have written on the board, right. Independence is a very important, again a very important concept which sort of flows from what we have already talked about, which is basically conditional probability. In other words, supposing you have two events A and B, right, and the occurrence of one of these does not say anything more about the other, right. Supposing you have A and B and which are, let us say, disjoint, right, then you know that if B has occurred, A cannot occur. So that is P of A given B or P of B given A will be 0, even though P of A and B by themselves will not be, will be positive, right. So that is saying a hell of a lot, right, that if, or if A and B are highly related, you know, if P of A given B can be very close to unity and things of that kind, right. But supposing you have this situation, i.e. let us say that in this case I am saying the occurrence of B, right. So that is P of A given B, supposing this is exactly equal to P of A. Supposing you have, let P of A given B equal to P of A, right, which is where of course P of B is greater than 0, right. So if this situation prevails, right, then you say that A and B are independent, right, but instead of writing it in this form, it is written in a slightly different form, right. So the alternate then this is how basically independence relates to conditional probability, but the way in which it is written is slightly different, as many of you have already encountered, right. So the alternate formulation is to say that P of AB, this is a condition for independence. So the, right, in other words, the joint probability is the product of the individual probabilities, right, and this condition works, this condition is, right, does not require P of A or P of B to be more than 0, right. So condition does not, right, does not need P of A or P of B to be strictly positive. So it works even if P of A or P of B is 0, why you cannot write this, right. This is okay as long as this conditioning event has non-zero probability, right, but supposing P of you know, you can all this is an easier way to remember the same thing, right. So because and these two are equivalent when P of B is non-zero, that is obvious because of the definition of P of A given B is P of AB by P of B, right. So so you do not have to remember this, it is enough to remember this, right. So independence is, right, means exactly of A and B means exactly this. So you can claim that, right, if A or B, either of them is the impossible event phi, right, then clearly this equation will be satisfied, and you can say phi is independent of any event, any other event, which is true. Or if A or B is omega, then also this equation is going to be satisfied. But those are extreme cases. In general, right, you have the situation where P of A is between 0 and 1, P of B also is between 0 and 1, P of AB again between 0 and 1, such that P of AB becomes the product. Then, right, you say that the events are independent, right. Now there is a common misconception that independence, right, is somehow the same as mutually exclusive or disjoint. For some reason this is this myth or this false conception is prevalent in many, you know, beginners, so we have to dispel that right up front, right. The two are completely in general different, I mean they are not, they are, but those two concepts do not overlap at all, right. If A and B are mutually exclusive, in general they cannot be independent, right, unless you take some well, let us not even look at the exceptions, right. So remember that, right, independence and mutually exclusive are totally different concepts, right? Okay. So, where does this happen in practice, or what are some very simple examples? If this question is asked to a bunch of students, immediately the answer comes, well, if I toss a die twice, the first throw is independent of the second throw, or and events of that sort. But you don't need a repeat, right, repeated trial like that, or a compound experiment, right, where you're actually combining essentially two different experiments. You don't need that. You have another example where, let's say, I'm just tossing a die once, right, and I can still define two independent events. Have you seen an example of that? No? Supposing I give you the identity 1 by 6 equal to 1 by 3 into 1 by 2, right? Can you construct from this identity? We all know that 1 by 6 is exactly equal to 1 by 3 multiplied by 1 by 2, right? Nobody is going to complain that I'm trying to pull a fast one on you on that one here, right? But now I'm asking you, right? Define A and B such that left side is AB, P of AB, etc., etc. What would be your answer? Come on.
The die roll is a multiple of 2 and a multiple of...
I want the intersection to be 1, right? So multiple of 2 and multiple of 3, only one intersection is only 1, and yeah, that would fit the bill, right? So this A could be the event that you got a multiple of 2, which is 2, 4, 6, or B could be, as per your example, B could be a multiple of 3, which is 3, 6, and clearly there is only one point in the intersection, which is therefore P of AB, right? So you don't require, right, a compound experiment to get independence. It happens quite often, right? Or for example, you have 1 by 52 equals 1 by 13 into 1 by 4. This is right, an even more obvious case, right? And I don't have to construct the full example. I think you can do it by yourselves, right? So the 1 by 52 would be a specific card in a 52 card deck, and 1 by 13 would be the suit that it represents, and the 1 by 4 would be the face value of the card, right? Whatever it is, A to 2, ASD, right? So for the sake of the camera, however, I may have to write a few more things. So this is right. So that whatever we spoke has been, right, put there. All right. So clearly, right, if this equality prevails and everything is non-zero, you can obviously divide by either PA or PB and get both of the conditional probabilities to be equal to the unconditional probability. That is, P of A given B will be P of A, and P of B given A also will be P of B. Both of them will hold. Yes?
What if we define B to be the probability of it being odd? Then will it be independent or mutually exclusive?
Obviously it will be exclusive, right? If you say B is 135, sorry, yeah, 135, you're saying B is 135, then clearly AB is 5. So obviously they will be exclusive and not independent. So the question is, right, if this is I'm not sure, what was the point of this is, you wanted to explain, look at independence and mutual exclusiveness is in the same example, right? If that is the point of the question, yes, right? 2, 4, 6 and 1, 3, 5 are exclusive. 2, 4, 6 and 3, 6 are independent, right? Similarly, for example, if I took A to be perfect square and B to be an odd number, then also you get independence. 1, 4 and 1, 3, 5 are independent.
Is it possible that probability of A and and probability of B are non-zero, but they don't have any intersection and it can still be independent.
That's only it can only happen if you take some extreme example or trivial example like A being A being phi, A or B being phi. Only then that equality is going to be satisfied. It's not going to be satisfied if A and B both have non-zero probability, right? This equality is satisfied only if A and B are exclusive, only if one of them has to be the empty set. Otherwise, it's not going to be satisfied, right? Definitely. Any other those latecomers here? Did you you're okay, right? All right. So let's move on. So A and B are exclusive. A very important result is that if A and B are independent, the important result is that A, B complement, right? A complement B, A complement B complement, all of them are independent events, right? So and A and B are independent, so are A complement and B, A and B. This is a very intuitive right result, because you don't want, right, if A and B are independent, you don't want B complement to somehow tell you something more about A than B, that B could not tell you, right. So to prove or to understand this a little more, let's focus on this example of A complement and B complement. Let's take that. The others you can do by yourselves, right. So this probability of, so what we have to show that A complement and B complement are independent, what do you want to do? You need to show, is it true that P of A complement B complement is, I'll put a question mark here above the equality sign, which is what, right, we are trying to show. We want to show that this is the same as P of A complement multiplied by B of B complement, right. This is what we have to show. So to proceed, this left hand side we use De Morgan's law, right. So which tells us that this LHS is exactly what? P of A union B, the whole complement, right, by De Morgan's law. Since A complement B complement is the same as A union B, the whole complement, right, and this is 1 minus P of A union B. Now it's interesting here, right, incidentally P of A union B itself now can be written in terms of just PA and PB, because we know how to write PAB, isn't it? So what is P of A union B? In this case it is P of AB plus P of B. I will just skip a step and directly write P of A, P of B here, because I know that this is, right, P of AB, I know that A and B are independent, so this is P of AB, right. See, so look how nicely algebra comes to our aid here, right. So what happens? You get a very interesting factorization of this quantity out here, which is basically 1 minus PA multiplied by 1 minus PB, and that is exactly this. So similarly the others, right, can all be shown with all the tools that you have. I am not going to right, spend the valuable time out here doing every little thing, right. So again the takeaway is very important, that is that if you have two independent events, right, you have more than just the two, you have all of these as well, right, and neither A nor A complement change the situation as far as B is concerned, and vice versa, okay, right, okay. Now what we want to do is extend this to 3 events, right. supposing I look at 3 events. When do I say the 3 events are independent? Now, I have more things that I can do. I can consider A and B C, or I can consider A and B union C and things of that kind, right? So I want not just pairwise independence, I also want something beyond pairwise independence. So first thing, of course, pairwise independence. We must have, for independence of A, B and C, we need, for independent A, B, C, we first need pairwise independence. What is pairwise independence? P of A, any pair should, right, the joint probability should be product. All 3 pairs, right, it should, the independence should hold. And then on top of this you want one more. What is that one more thing you want? We also want P of ABC to be the product of PA, PB, BC. We need 1 and we need 2. P of ABC to be equal to PA, PB, PC. Why are both? Why is all of this? So basically, we have 4 conditions now. 1, 2, 3, 4. Why do we need this one? All 4 conditions are needed if you want A to be independent of B union C, A to be independent of. Say for example, from this you can clearly see that A must be independent of B and BC, because P of B into P of C is P of BC by this condition here, right? So clearly A is independent of BC if you put all 4. Likewise, you can show that A will be independent of B union C also, right? So to get any possibility, any such combination, right, to come out to be independent, you need all 4 conditions, right? So it's very easy to come up with examples where you have pairwise independence but you don't have real full independence, right? So if I consider a simple example like this, which I have again taken from some book, if I have, let's say, some strings of letters that, right, let me make sure this is, I have to do it very carefully, so I need to take this paper and make sure I don't miss anything. If I have some strings of characters and I am going to give them all equal probabilities, I have basically these are now not events. A, B, C are just some 3 characters I am writing down on a piece of paper or something, and right, I am going to pick any one of these strings with equal probability. How many strings? I have 9 strings, right? A, B, C, A, C, and the order is very important. A, B, C, B, C, A, B, A, B, C, A, C, B, B, C, A, B, A, C, C, B, A, C, A, B. So I have 6 of these, right? 6 permutations of A, B and C, all 6 permutations are here, right? Then I have 3 more, A, B, 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 C, C, C. In other words, let's say that I've written these character strings on 9 pieces of paper, right? And then I jumble them up, right? And pick any one of these, right? A piece of paper out of a hat, right? So I will attach a probability of 1 by 9 to each of these strings, right? So equiprobable points. So these points in omega are equiprobable with probability of 1 by 9. Now, how do I define A, B and C, right? I am going to define capital A, the event A, as the event that letter A comes up first, and so on with B and C. Oh no, sorry, no. A will be, okay, let me write it down. So continuing this example, let A be the event that A comes first. and B the event, by definition the event that A comes second, right. Again I have to make sure I don't mistake this, and C the event that A comes third. Now you can check for yourselves that A, B and C are pairwise independent, right. So for example, if I pick this, right, this string, then my event A has happened because A has come first, right. If I pick this, then the event B has happened, right, because A has come second. But what is the probability of the event A, right? It's clearly 1, 2, 3. So this will say that P of A will be equal to P of B will be equal to P of C is equal to 1 by 3. So what is P of AB now? AB will be A coming first and A coming second, so it's only happening here, right. So you can clearly see pairwise independence in action, right. 1 by 3 into 1 by 3 is 1 by 9, so pairwise independence, right. But do we have real independence? No. What is the probability of ABC? Still 1 by 9, which is not 1 by 27, right. That happens only if you pick this ABC, there is a point here, right, where A comes first, A comes second and A comes third, right. So which is not equal to ABC. Likewise, right, you can come up with many examples, some of which we will put on the homework also, right. The first homework set will problem set will contain things of this kind, right. But for the sake of the not independent, right. So you can extend this to more than 3 obviously, right. If you extend, you have to make sure that right, you have to start from pairwise, then go to any combination of 3 events, then go to 4 and so on. So obviously as you keep increasing the number of events in the family that you are looking for, overall independence, the conditions will keep on growing. The number of conditions you have to satisfy will keep growing, right.